keynote speaker is Dr. Thaweesak. He is a professor and head department of media technology, King Monkut University of Technology, Thonburi, Thailand. His main research area is in the field of processing automatic speech recognition, energy-based voice and unvoiced detection, acoustic feature extraction, applied statistical analysis on emotional speech, spectral analysis and modeling of vocal tract characteristics for emotional speech, and many more. Now, not taking much of your time, I would request Dr. Thaweesak to please commence with his session. Dr. Thaweesak?
Yes. Yep. Okay. Can you hear me?
Yes, sir, I can hear you.
Okay, okay. I think I'm going to share
Thank you so much, sir. We
screen.
welcome you all in this international conference on data science and machine learning, sir.
Okay, thank you very much for inviting me to be the another keynote for this conference. Okay. I'm Dr. Thaweesak. I'm from Bangkok. Actually work with the KMUTT. Can I start now or hello?
You can start, sir. You can start.
Okay, okay. Thank you, thank you. Okay. Today I would like to share with you with some research that I'm conducting with some colleagues from the Vanderbilt Medical Center in Tennessee state in the U.S. And we keep continuing on this research. So I would like to share you. It might be very specific topic, but I would like to share you, and this involved with the machine learning, which is the theme of this conference. Okay, so I will start my slide here. Can you see, right? Can you see screen, right, Doctor? Okay. Okay, the topic that today I would like to share is about actually apply the machine learning to in the work of the how to predicting the depression levels in the some patients which have the emotional illness, and the motivation is that we try to determine the suicide risk that is actually be the long-standing problem in the suicide prevention. So this will actually scan on the topic that how we're gonna prevent the people to committing suicide, and how we're going to take them into account to give them the right proper treatment to cure that depression. And we try to making the database, the large database on the sound recording based on the key adjustment by help of the psychiatrist to in the recording of the data, collecting the data. And the motivation to this research is just suicide is a really high ranking cause of the death in the US, in the Thailand, or in the society in the world. So that the treating cause that every society facing up now. And the current suicidal risk assessment is done only on the clinical judgment level, and the objective diagnosis too are still limited. So we try to finding the technique and the way to investigate this problem. Try to find the tool that can help psychiatrists to work on their work more easier, like a diagnosis subject or patient before we admit that to the hospital for have a good treatment, a proper treatment to the symptom level that we evaluated. I mean, the group of the psychiatrists, I'm the one just like a collaborator in that team. And okay, there's a hypothesis. Actually, we try to like apply the speech processing technique to help the psychiatrists to complete their work. And this is like this research is like a collaborate between the engineering, all the staff, all the colleagues from the department of the electrical engineering, biomedical engineering, and also team up with the Medical Center, which is some staff have like we have the long collaborate on this research work, and we try to find out and figure out. And some part of that, we also have the PhD candidate student that come and join force and try to figure out the better way to overcome this problem. And this is a hypothesis of our research that suicide patients at the near term risks exhibit significant perceptual change in their vocal quality. That means there's some quality of the sound that is spoken out. It changed from when compared to the normal speaker. That's the hypothesis. And the objective is that we try to investigate the validity of the using the vocal property of the speech as a diagnostic tool for assessments of the suicidal risk, and try to develop the robotic independence classifier that capable of the differentiate the different vocal quality from different characterized group of the patients. Try to find some significant difference in the acoustic property between class, like the suicide one, again the normal speaker group. That's the objective. And this is the idea of the research procedure that we have planned and already done so many times on the increasing of the amount of the database that we collect day by day. And on the left, that the speech database that we formulation, and then we try to extract some feature from the spoken sound that we record from 3 different. That's the basic 3 different group of the speaker, which is the normal one, that actually the control speaker and the patient with the suicidal risk, the group that has been already tried to committing suicide, but failure by some rescues from the maybe from the family member, or maybe from the officer in the time that they tried committing suicide, and someone make a call the hotline to the police department, and then they came to rescue them. And the third one is the normal depressed patients who have voluntarily enroll in this program and in the record of their sound sample. Okay, that's the left of the database formulation, and then we extract all that based on the some specific vocal feature, and then we use that in classification by training, and then test it on the model that we have based on the distribution of the feature sample that we extract out. We have to look at that distribution, and then we try to find the pattern of it, and then use that as a pattern classifier to see how they are accurate based on the acoustic feature that we use. And this is just show you of the database. Actually, the only 10 mail that we use in this work, but we still collecting more. And this just show you the different characterized. The first one is a major depressed, based on some criteria, and some score from Beck and Hamilton. This is gonna classify based on the judgment by the psychiatrist and the doctor. Help in this work to identify all the subject that participate in this research. By looking at the score, if it's higher, okay, it can identify as a major depressed. This normal one, the normal one right here. That means the score less than 7 or less than. And in the middle is the term of the high risk. This group of the high risk. This is really, really rare to find. But this speed sound record, we record within a minute or week from the time that they had the suicidal attempt. Okay, these are the difference of the database that we use in this study and to figure out how accurate of the our classification can provide us. And this just show the detail of the how we first pre-process all the data first, like use the same sampling rate when the time you collect, and just get rid of the 0.5 second of the excess part of the silent. That means we remove this out, and we also try to develop the algorithm that can like automatically delete all the parts that longer than 0.5, and then we collect all that for the further step of the vocal analysis. And this is actually our research work is based on the this model of the speech of the human speech productions. That means we try to looking for the model of the our how the voice is generated inside the production system, and we try to represent try to find the feature that relate, that can present the work, the process that inside our speech production system. And we can like separately, mainly into two groups. The first one we call the source domain, and the second one is the filter domains. The source domain is consists of as you can see, the first step is start from the impulse chain generator, and then it's part of some model that represent the glottal parts. That this part is like a voice. Okay, the part that generates the voice section in our speech. Actually, in our speech, it's contained with 3 or 4 parts. The first one is the voice, unvoiced, and the silence. That are the 3 main parts that combine together in our speech when every time we speak it out. So this is the idea of how it produced inside our speech production. And below here is like a random noise. This actually for all the stem also have the noise that combine with intentionally or unintentionally. They're always there, all right? And then they mix up together. When it come out, it will pass through the vocal text model. This vocal text model that we call the filter domains at the end of the part where our sounds come out from our lip, and then we have that outside the speech. This is a model that we try to find out for our feature of the acoustic feature. And what we do is we separate into domains, and then we focusing for each domain. For the first one is the sound, or sometimes we call it excitation domain. And this one we're looking for the Jitter parameter, the one that calculates based on the fundamental frequency. And the second one we call the Glottal spectrum slope, that related to the emotional state. So we try to measure this from those 3 groups and use that as the acoustic in our classification. And the second domain we call the vocal text. This one we try to estimate for the MFCC the coefficient that related to the frequency response of the vocal text. That two domains combined together, and then we put in a classification and see how is the input for the accuracy. And before we doing that, first we have to kind of like measure for the statistic property of the feature samples that we extract by first using the sample range testing to compare between the group distribution by user F test for variance and T test for the means to compare among three groups that we extract. And then next what we do is we classify it using the probabilistics modeling of the feature distribution. This one we try to fit some model order to on the feature we extract, and to see how fit of the model, how the sample is distributed by applying the first one, the unimodal Gaussian model. And if it's not fit well, so we try like a mixture of the Gaussian component, maybe more than one or two or three. It's up to the fitting that we apply to the sample that we extract. When we have that, and then next what we do is we try to classify to find accuracy classification accuracy of the probabilistic that we have, and then evaluate it based on the training and testing. Okay, I will go to the first domains is source domains, and what we use in this domain is that the first one is the vocal register. The definition is a measure of the variation that's found within a successive period of the language vibratory pattern. The motivation is that it can measure the stability of the phonation and was predicted to be more elastic under emotional state. That means it changed when your emotional level is changed from the normal to the deepest, or even worse to the really severe deepest, or in a minute of that you like have the idea tied to committing suicide, kill yourself. That change a lot. So this is a motivation of the Jitter parameter that we use. And the idea is that we try to apply just some technique of the wavelet transform to apply it, and try to estimate the Glottal cycle duration from the segment of the voice speech. And this is just the idea that what is a wavelet transform is that we just like doing like a decompose of the frequency component of the signal, of the space signal, and then look like we use many of the filter for the high pass filter and low pass filter, and then it's like a scale concatenate of the scale, and then we try to look at the energy that come out from each state of the filter that we use. And this is just show the idea of that which scale that we select for the to looking for the fundamental frequency of the voice segment of the speech signal. And as you can see here, this is a frequency response of each scale that we use from the first to the fifth, and this fourth scale just represent like have a behavior like a band pass filter. Just only this scale. The first one is look like a high pass filter, and as you already seen is that we use the FS sampling frequency at the 10k hertz. That means the highest frequency that we can expect from the spectrum analysis, that is about half of that is a 5k hertz. Okay, and When we have that, the fundamental physics, we can use this for the Jitter parameter estimation. And this will just show you that for the different energy that based on each segment that I told you that for the first one is voice and silent, they have the different amount of the energy. So this the energy weight that we can use and then can like detect it, identify each segment of the speech. And actually right now we just stick to the voice segment, which is high energy when compared to the unvoiced or the silence. So we stick to the, but some researcher with the related work also just comment that, okay, in the silent and unvoiced also have some information that might be helpful. So we're gonna take these two is the account for the further study of this research on the continued work. And these are just the idea of the how you estimate the vocal register, because it's all based on the fundamental physics. If you have that, and then you can estimate the vocal register. And then first we have the acoustic feature that we're going to use in our classification. And this came out from after we extract that, and then we look at the distributions. This is a class distribution from each group of the volunteer, the patient, the subject. The first one is the normal. We label it as the total and depressed and the suicidal. And just show, and then we test all the statistics here for length test, F test, and T test. And after that, we just use only the single extract feature based on the jitter in the classification. I just show the result that from the classification we showed about 80% between the control with the suicide versus the suicide. That's about 80%, and that's a very lower for the other pairwise classification. And that's the result from the first acoustic feature that we use based on jitter. And next, what we do, we try the second one, the Glottal flow waveform, the Glottal flow slope. And the definition, the motivation is that the shape of the flow waveform was predicted to be altered. Doesn't mean it changed based on the result of the excessive tension and the lack of the coordination in the musculature under emotional state. That means it had some effect on the slope for the emotional state. So we use that as the motivation to extract the slope. And it's just the idea to show you that for the slope that in the under emotional state and the regular normal emotional state, it just show the slope that have some degree that change, have some difference, can notify that. So we use this as our second acoustic feature. And this just idea that for the outcome of the work of the speech, that when we speak out, the spectrum or frequency response, it just show like on this column, as you can see. But what we try to measure is the Glottal slope is deep inside in the source domain. So what we try to do is that we have to eliminate the response, that the frequency response that came from the vocal text. If we can eliminate this, we can get the waterfall slope here. That's the idea. So we have to eliminate all these vocal text, and then we're gonna get the Glottal slope here. That's the idea. And when we doing that, we having that, and then we also try to look at the sample, the distribution of sample from 3 different categorical groups, and it just show some significant and also have some the outline from this from the suicide. And then we also test all of that for the length test, F test, and T test. Okay, and then we also do under classification, I just showed that about 90% in based on a single Glottal spectrum slope between the normal versus the replaced speaker. It show about 90%, and for the other is lower for at the 75 and 60. And next, what we do is we go deep out to the vocal text over here for the filter domain, and then we extract that using the MFCC. The idea is that first, that we have to do like a transformation by the custom, and then we just filter it out using some the filter banks, and then we get the energy. The motivation is on this MFCC is that it can provide a robust spectrum response representation of the speech spectrum, and they can easily be compensated in the case of the when we have like a different recording environment. This can like compensate that, and the Mel scale is incorporated in the estimation to better capture the perception important characteristic of the speech. That the motivation, and then we like I said that we use a filter bank, try to filter out and get the energy from each filter. Over here we try to get about the 16 coefficients by using the triangle filter apply for each small bandwidth, and then we extract it. But for the upper plot that you can see here, this is like or the filter bank is respond in like a linearly, but based on the our sound perception is that our ear is not respond, don't have the like a linear frequency response. Actually, they have some part they have the linear, but when the frequency is higher than 1 kHz, it behaves like a nonlinear. So we try to adjust it, not to be the nonlinear filter bank that apply to the capstan, and then we get the energy out again. And all the energy that we have that represent for, we call it here the capstan coefficients. And we have tried it, okay. And this one, it just show you a distribution. Every time we have to look at the distribution before we apply the model to see how it fit. The distribution model, how to see how they fit to our sample that we extract. For the first one, you can see this from the normal speaker, and this one from the major DPS, and the lowest part is just show you this one is for the highly suicidal, which is that you can see the different model. That means they have some can use more or many component in the model. That's the idea. And okay, and next what we do, we try it. Like we try, we observe it on the distribution, then we try it on the numbers of the Gaussian component. We tried on the 2, 4, 6, and 8, and look at the performance from the classification and see. And the best performance that we can.
Thaweesak, sir, I'm interrupting you. Next speaker is waiting, is online. So could you just wind up fast, sir?
Oh, okay, sorry. Okay, I will wrap up. All right. I will finish in a second minute. Sorry. Sorry for spend more time deep in the content. Oh, no problem. All right. Okay, I think I'm gonna go. That's the idea that, okay, we're doing that, and then we classify it, and then they just show you, okay, just a couple of slides. I just show you that for the Gaussian model, it gives us a better performance when compared to the unit model. So we stick to that, and then we do the classify, and then we combine together for the two domains, as it come up that all the classification accuracy is all improved for all the pairwise classification. It's about 90%. For the DPS against suicide and control against suicide. So these are indicate multi-parameter classification result that you show. So that means if we find more technique from the machine learning in the term of the classification, and also the develop of the speech processing technique, and combine together in this work. I hope that more improvement we will can get from our future work.